Yeah? You alive today? Nobody can be falling asleep on me? So how many of you are planning on coming next week for effective design review? Anybody? Good. So it should be a big change up from these last few that have been more about documentation. So it should be fun, I think. But today will be still kind of in the heart of this documentation talk that we've been doing. So we started with user needs. We talked about specifications. I guess we did a little project management in the beginning. So all kind of engineering meat and potatoes. This is stuff you'll spend most of your careers doing as engineers. I know it sounds scary, but it'll be more than half your time. The times when you get to do what you do up in the lab and build and design will be a small fraction and the part that you really love, but this is kind of the necessary evil. Hopefully that mouse doesn't keep bouncing around on me. So this is specification development. This is our third lecture in this series. So we'll jump in. You're all returning students, so I assume you know what specifications are to some degree, but we'll cover it and why they're important. How many of you have seen videos of like engineering disasters in the past in some of your lectures? It usually gets covered in a couple of lectures. I'm going to cover a couple of those. One is the Tacoma Narrows Bridge. And we're going to go over those real briefly. I assume most of you probably have seen that one at some point. If not, you should. It's spectacular engineering failure. It's kind of one of the historical standards of engineering failure that everyone points back to. Another one we'll talk about is more recent with the General Motors ignition failures. So both of these were failures of poor specifications. Okay, so they had the user needs, but they failed in specifications. We'll talk about some types of specifications. That'll help you figure out if you've got them all. We'll talk about some industry standards and how those affect your specifications. Doesn't come into play in a lot of EPICS projects, but it does crop up. And when you get into your professional lives, it definitely crops up. And then we'll talk about a tool called functional decomposition. And this is a way to make sure that you've got all of your specifications. Okay, no foolproof way, but it's a good tool. So we'll jump right into those two examples, starting with the Tacoma Narrows Bridge. We've got little videos on those. So just watch the videos as we go through both of these and try and pick out. So you'll see how it failed physically. Okay, try and figure out how the engineer failed when he designed it by specifications.
Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So they were using this bridge as it swayed like this.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
So I think the music gives that a little good gravity. So, so does anybody have any idea what was the specification they missed when they designed this bridge? What did they fail to account for? Benny, go ahead. Wind, yes. So in their user needs, do you think they had wind, being able to withstand wind as one of their user needs? Absolutely. I'm sure they did. I mean, if you're building a bridge, like what's affecting my bridge, right? Gravity, wind. Pretty well, right? So, so the problem was they had the user need and they failed in their specification. They failed to account for how much effect it would have, okay? It was a function of the understanding of bridge design at the time. They really didn't understand that you could get into these kind of situations where you're getting basically a harmonic effect in the bridge, right? So we'll jump into this little bit more modern equivalent view and try and pick out the spec failure here.
Jake Fisher, Director of Auto Testing at the nonprofit Consumer Reports, is showing us why 2.6 million GM cars are being recalled.
how easy is it going to be for me to accidentally turn off the ignition, put it in accessory? Depends on how much is hanging off the key ring. Right,
After a tug on the keychain, I deliberately steer the car back and forth.
the power steering is gone.
But there's a loss of engine power, power steering, and power brakes.
It is not easy to avoid the cones. I did it, but it's not that easy. How much effort did you have to use in the steering wheel to get around that? Quite a bit.
The flaw in the ignition system makes it possible to turn the key off accidentally. On the road, it can lead to an anxious moment, sudden surprise, or worse.
Start the engine up, put it in drive, and as you're driving, there's a heavy weight here on the key. You get a whole lot to actually turn that off. Once that happens, you can't start the car anymore. Worse, you lose your power steering. So you lose control, and if you're in the off position, your airbag's not going to play.
We tried the demo 6 times. When the engine shut off, the Cobalt was harder to control.
All right, there it goes. Now I could go around the cones, but I knew the engine was coming.
What's the worst case scenario here with this car? The fact that they're still out on the road.
Well, the worst case scenario is, when this happens, you lose the ability to actually steer the car very well. You could lose the ability to stop the vehicle, and you are highly distracted at that time. Along with that, you have the airbags are shut off. So it's very easy to see how an accident can happen and it can be very tragic.
So accidents did happen with that particular failure, and it was a significant issue, caused recall of millions of vehicles, and a lot of executives from General Motors were pulled in front of Congress to testify as to why they didn't catch this and why it took so long to fix it. Anybody guess what was the specification that they messed up here? It's pretty straightforward. Anybody? None of you? Right? So when you're designing the ignition switch, right, you have a user need that it should stay on, and you say, if I apply a certain amount of vertical force, it should be able to withstand that, to expect the weight of a set of keys with some of the weird stuff people put on their keys. My wife's keys weigh like 17 pounds. I don't know why. She doesn't have a lot of keys. I don't know what makes it weigh so much, but you can't put it in your pocket either. It's like this big, drives me crazy. I can't drive her car just because of that. So the rating, when they did that, they said it should be able to withstand a certain number of pounds. And there was some engineer at General Motors of our generation who wrote the specifications for this car and failed in that specification. They got fired. A lot of engineers got fired in this, and I'm sure that they really have struggles knowing that people have died from that failure. And I'm sure they didn't do it on purpose. I mean, I'm sure they went through and did their diligence, but these things happen. It's very difficult to get all of your specifications correct. So that's why we stress this so much, right? So specifications are vitally important in engineering design. You guys can build really cool stuff without writing user needs and building specifications, but you're much less protected from things like this happening, okay? Use civil and mechanical examples because they're dramatic, but computer failures are everywhere, and they're often caused by poor specifications. So don't think you're exempt because you don't have a bridge to fail in front of everybody. Those issues are just as big. And even if you're in like a consumer product industry where no one could get necessarily hurt by your device, you can still have a failure commercially and cause a big significant problem to your company, or people can lose jobs and things like that, okay? So as engineers, when you design a product, it's for a company, it's usually a lot of money involved and a lot of people's jobs involved. So you want to protect those by being diligent. So specification is very important. So what is a specification? Translation of a user need into objective measures. What's a user need? You guys were mostly all here last week. What's a user need? It's one of the primary features of a product, right? Primary features of a product. Sound good? So specification, you're taking one of those primary features and you're giving it quantitative measures. So you're wanting to say, how can we specify what this is in a quantitative way and be able to make that translation. So this is what you're going to measure yourself against after you design, okay? So when you go to do verification at the end of your design and you're testing a design, you're going to test against your specifications. So if your specifications are inadequate, you can pass those tests at the end and have the device fail because you specified poorly, okay? So sometimes you want to do a lot of analysis before you make a specification to figure out If I'm building an airplane, I'm going to say the wings should withstand a certain amount of shear. You better know what that shear is, right? And give it a good safety factor. So sometimes it takes a lot of work to get there. We're going to go through 3 types: functional, interface requirements, and performance requirements. I think it'll be apparent to you guys what these are as we get into them. So functional requirements specify what the product does. So this is one of the simplest ones and usually the first one you think of, right? And we talked about a kite last week. Well, the very first thing we had was it should fly, right? Functional requirement. So that's pretty basic. And you're talking about what is the right output from the system given a set of inputs. And everything that you might design is a system that takes inputs and gives outputs. It may not be obvious at first. But if we kind of abstract this, tie into all that great math you guys take that you won't use. So if our system is a function, right? It's having some outputs like y and inputs x, okay? Functional requirements are interested in what is f. So what is that function? What are you doing? All right? So that is the system. If we take a look at interface requirements, these specify how the device will react with outside systems. So are there mating pieces or internal systems that it has to mate with? You're also interested in human factors at this point, okay? So if you have a user interface in a piece of software, a user interface on a piece of hardware, what are those user requirements? What about size and weight? How does it look, right? So industrial design comes a lot into interface requirements. Ergonomics, is it easy to use? So we think about this abstraction again from a math standpoint. Interfacial requirements are interested not in what the function is, but it's interested in how does the function take in an input, and how does it present you with an output, okay? So people who do software, this is probably really obvious, because you write actual functions. So you say, okay, I've got a function that I'm writing a piece of code. I'm going to have a null function. It's going to give no output, or I'm going to produce an output, and you're going to pass information into the function and get an output. So it's that black box concept, right? I'm going to give you something, you're going to give me something back. And what that system is that you're passing in and out of, that's your functional requirements. Your interfacial requirements are the passing. So if you think about a computer system, you've got inputs coming in from a human, from a keyboard or a mouse, right? So those are your inputs. Your outputs are a monitor, speakers, things like that. You may think if you're doing something mechanical that doesn't make sense. I designed knee implants in my previous job. So what would be the inputs to a knee implant if that is my system, right? Knee arthroplasty. Any guesses? What are the inputs? Muscle forces, gravity, reaction forces, right? Things like that. The bones.
Impact on the joint if you fall or if something hits you there.
Exactly. So you have those, and what's the output? Functional system, what's the output? Motion, generally, right? So I apply muscle forces with my hamstrings, my knee flexes, okay? Or I have inputs of a force on the joint, and the output is pain to the patient. And then what's the system? That's the articulation between the joints, generally, right? So I've designed a femoral implant and a tibial implant. So tibia is my shin bone, femur is thigh bone, and those interact on each other. And depending on the shape of those, that function, right, I'm going to get a different output from the inputs. Okay. So mechanical systems work just the same way. You can abstract them the same way. So those are the things to consider. So as you're coming up with your specifications, and you can kind of use this thought process for user needs too. Think about your function, and then think about what are your interfaces. And the idea of doing this is just to break it down so you can consider all of the specifications that you'll have. Okay, you're just trying not to miss any. So yeah, interface is kind of a boundary condition issue. So performance requirements are a little bit of a different animal, and these will fill out a lot of your requirements. So functional requirements aren't interested in what the function is or what the inputs and outputs are. It's interested in how well the function does its job. Okay, so if your function is y equals 2x, and your function is actually 1.99 or 2.01, that's what you're kind of specifying here. How well do I get the right output? Okay, so in performance requirements, you're interested in how much, how well, what is the speed, strength, accuracy of what I'm doing, right? How well does it do it? You'll be interested in things like the reliability and safety, the service life, things like that. So there's a whole bunch of these that go into performance. So I listed a bunch of them on the right-hand side just to give you some idea of what we're talking about. So what's the temperature range? What is the shock that it might have? In an electronic system, what are the noise levels, right? So in any real system, you have noise. You have inputs and outputs that are being pushed away from their natural levels. What are maintenance, shipping, packing, all these kind of things fall into those performance requirements, right? So the function is doing the same thing with the same inputs and outputs, but you have to make it a different way. So these are the things to consider. So that right-hand list is not exhaustive, but it will give you a good kind of brainstorm when you go in to do your specs. Say, did I think about the environment, right? I'm designing a piece of electronic hardware that's going to be used in Africa, and the humidity is 90% all the time. Did I design it to be used in that environment or in the lab over here? So things like that you want to consider. You want to consider the real-world system where it will be used. Does that make sense to everybody? So those are the main kind of spec types. So once you've written your specs, you want to think about evaluating your specs. You want to go back and self-evaluate. So the first thing you want to look for is, are my specs unambiguous? And that is to say verifiable, okay? So every spec you have at the end of your project, you should verify. So that should have a quantitative test measure to say, I satisfied or did not satisfy, yes or no criteria, okay? The other thing you're looking for is, are they self-consistent? So your user needs, we allowed them to conflict, and they always conflict, right? So we said performance and cost. Those always conflict, right? More or less. So I want this thing to be the fastest moped on earth, but I also want it to be under $200, right? Well, those conflict. Now when you go to do specifications, you'll say, I want it to be fast. It should go 30 miles an hour. And then when you go to do cost, you say $200, and now maybe you can make that happen, right? So your specs should never conflict, even though your user needs can. So you're going to specify to a level, you know, my user need said it should be great. I said, here's how great it needs to be. I said it should be cheap. Here's how cheap it should be. And those should never conflict. So you should always be able to pass all of your specifications. They should be specific to use environment. We talked about that a little bit, but that could be physical environment like humidity, or it could be a use environment, right? So in a surgical operating room, or you know, in a facility where children play, right? Different environments, and they should be specific to that. And again, they should include pass-fail criteria for verification. So you should explicitly say in your specification, you know, it should weigh less than 10 pounds, and you should be able to measure that and say yes or no, okay? So make sure you keep those pass-fail criteria in there. So industry standards, just a little bit. You guys won't encounter a whole lot of these in EPICS. When you get into your careers after EPICS, you'll encounter a whole lot of these. Some EPICS projects do require them. So things like Habitat for Humanity, you have building codes, right? So industry standards, they specify expectations across manufacturers. So no matter who's making something, that you have a common set of ground rules. And that's usually for times when you have pieces that interact across systems, okay? So three kind of big types of those technical specifications. You have interface specifications. So that's things like the threads on a screw, right? If everybody made threads on a screw differently, the world would be a very complicated place, right? So a long time ago, people got together and made standards for screw threads. So if you can go and buy a number 10 screw or bolt, it's going to have the same thread. And there are a lot of variations on those actually, but they're all very tightly specified. So you can look up in detail what threads are. So those are kind of interface standards. Material standards, things like tell you how a material should be made so that you know when you as an engineer buy a material to make something, you know what you're getting, okay? So if you're going to make something out of type 17-4 stainless steel, it's going to have a certain amount of chromium, certain amount of vanadium, certain amount of carbon in it, and all be allowable ranges. And it'll say it needs to have a certain hardness, strength range, things like that, okay? So those are the things that you're looking for in a material standard. All these types really affect standards or specifications, because when you write a spec, if you can reference a standard, that is always good grounds for your spec, right? So if you are designing a knee implant like I used to do, you can look up ISO standards on, you know, how to test a knee implant, things like that. How thick the polyethylene bearing should be in the implant. So if you follow those things, you'll generally have success. If you don't follow them, you'll often get into trouble. The next type, standard operating procedures. They're manufacturing standards, tells you how to make something the same way as everyone else. That can be important, not so much for you guys right now. And then method or practice standards, these you might run into. So these are kind of ways of doing things, right? So if you go in to see a physician and they go through a specific set of questions when you present with like an injury, they're looking at, they've built as a community a set of standards of methods of doing where they're going to look at the most common and most serious things first and then go down the list, right? So important thing to understand if you get into those sort of ways of doing. And then the most common one that you'll interface with is the last one, testing standards. So this will be a standard that says if you are building something, here is the test that you run, right? So if you're building this chair, right, it's going to tell you this chair needs to support a still load of 350 pounds. And this chair needs to be able to support a dynamic load hitting it at 3 miles an hour of 290 pounds, something like that. Or it'll give you a fatigue test and tell you how to run it. So those are the kind of standards that you'll run into a lot. And as you design devices, you'll get into that. There are a lot of standards organizations, and they're really dependent on your field. So ISO is kind of over more or less anything. ASME for mechanical engineers, IEEE for electrical engineers, sort of thing. One thing to know about these is they're generally behind the technology curve. So I've been on standards committees, and they'll meet like once or twice a year for a short period of time, and they have a lot of work to do to write a standard, and people disagree. So it might take 4 or 5 years to write a spec, and you usually don't get around to that point until it's an established thing that you're doing. So if you're on the cusp of something brand new, there probably won't be a spec, right? So if you're designing one of the soap cars, you might find a lot of automotive specs, okay? If you are designing something that's never existed before, like the Braille reader, right? You're not going to find a spec for that. You'll find specs for the pattern of Braille and how tall they should be and how wide they should be. Those are things that you should follow, but you're not going to find specs for things that have never existed before, okay? They're just a little bit slow. Not that there's anything wrong with that, they probably should be slow. Okay. So that's most of what I had on kind of the nuts and bolts of specs. I'll talk to you a little bit about how this fits in the design process overall. A lot of these next few slides will be my personal opinion and not the official opinion of anyone else. But I want to share them with you. I think they're some valuable insights. So if you look at the design process, everybody's seen this picture before, right? It's in all the labs, okay? You start with project identification. You're meeting with your project partner, figuring out what it is you're doing, trying to understand your advisor when he tells you what your project is, and you've never heard of this before. And you go through that whole set, and then you get into specification development. You're creating your user needs like we talked about last week. You're developing your specs like we talked about this week, right? So you're putting all that together. And then once you're done with all that, you're going to start conceptual design, right? So the assumed theory here is that you haven't thought about what your design will be at all until you're done with specification development. I ask, is that realistic? Okay, so I'm taking my kids to Disney World in December, okay? And my son, he's 2. He's an inch too short to ride all the cool rides, right? So he can't get into Splash Mountain or Tower of Terror or any of the cool big stuff. He's an inch too short. So I want you guys to design for me something to make him look an inch taller. Go. Who's got a design? Who's got an idea? Right here. Wrong. You're supposed to say, first I need to identify what the project is. I need to interview you and your son to find out what your user needs are. Right? I need to interview Disney employees so I know what their needs are, their stakeholders. They don't want me to fly off the ride. And then you're going to write specification. Right? None of us do that, right? If you don't hear a problem statement and immediately think of a couple of answers, you shouldn't be an engineer. At least you're not like, you're either the perfect engineer or you're like an engineer I've never met before, okay? So that's just not realistic. But what happens all the time and why this becomes a problem is because we latch onto those ideas, right? So now you're like, it's gotta be taller shoes, when maybe the right answer is a wig that has an inch of padded foam, right? So it looks like he's got a really tall forehead. He walks around like this. Maybe that's the perfect solution. But you've zoned in on your solution and you chose right up front. And I don't know an engineer who's not guilty of doing this. I do it. You know, I sit in a project meeting with a team, and they all coming up with an idea, and I've got my idea right away, and I latch onto it, and I try and push them that way. But the problem is you isolate yourself, and you close your mind off from all the other ideas you could have. So the reason why this kind of process has been developed in engineering, and why engineering schools teach this, is because it works really well. And if you follow it, it works really well. But what I would encourage you to do is not fight that temptation to come up with ideas in the project identification stage in the first 5 minutes. But what I would advise you to do is fight the urge to go and execute those ideas, right? Don't come back in the lab and build it just quite yet, or at least don't spend a lot of money doing that. If you want to do it, great, you can build a prototype real quick. Does that make sense to everybody? So write those ideas down in your notebook. Don't fight that feeling, or you're not a human or an engineer. But so you'll see people like me come in and you'll have a design too early, and we'll tell you, no, you shouldn't have done that yet. We're not saying you shouldn't have thought of that idea. We're saying you shouldn't have run with it quite yet. Okay. So there's my thoughts on that. Which brings me into a next little bit on formal design, formal engineering design. How many of you have read Zen and the Art of Motorcycle Maintenance? One. So you all should read it. I think every engineer should read this book. It's fantastic. But I was a philosophy minor, so maybe I'm a little odd. So it's kind of a philosophy of science and engineering book. It gets a little weird at times. But I'll read it to you because it's a little bit hard to read up here. If I don't lose my voice too bad. I see a lot of tinkering go on in the lab, okay? So that is exactly what I'm talking about, where you have that idea and you go in and you want to build it. And that's good because you're coming up with ideas and you're building them. What's bad is when you say, I designed this and I'm going to deliver it to my project partner, and you don't have user needs or specs or verification and validation because you don't know how that thing's going to perform in the real world, right? So that's the urge we all have, like, I got an Arduino, I'm going to go build this thing. It's cool. Take a step back and think about this process and the engineering process we talk about. So I've edited this a little bit. So this is a quote by Robert Pirsig, who wrote this book. And he's talking about the scientific method. So I've edited it to the engineering method. And by that I mean the formal engineering design process, okay? When I think of the formal engineering method, an image sometimes comes to mind of an enormous juggernaut or a huge bulldozer, slow and tedious, lumbering, laborious, but invincible. It takes twice as long or 5 times as long or a dozen times as long as tinkering, but you know in the end you're going to get it. There's no design problem that can stand up to it. When you've hit a really tough problem, you've tried everything, you've racked your brain and nothing works, and you know that nature has really decided to be difficult. You say, all right, nature, that's the end of the nice guy, and you crank up the formal engineering method, okay? So if you do this the right way, you step through each step in the process, you can solve any problem within the bounds of physics, right? Okay? So that's my kind of strong-willed advocacy to the formal engineering process. Please really use this stuff. It really is valuable, okay? You'll be much better engineers. You'll be real engineers when you follow this process, okay? So with that being said, there's a kind of a modern movement these days towards something often called like Agile Design or Agile Engineering, which is one of many kind of ways of thought of trying to do things quicker, get away from some of the red tape. The reason for that is a lot of big industry has buried the engineering process in red tape. Okay, so I know one of the rival companies of the company I worked for, their engineers would quit there and come to our company and say, I spent 90% of my time doing paperwork. Right? That's not good use of an engineer's time. You guys are brilliant people. You should be designing things. We want you to document so that you can understand what you're doing and why you're doing it and make sure you're doing it well. But you shouldn't be doing nothing but documentation. So I agree with those Agile people a little bit, but they can get a little too far the wrong way. I think one big consideration that formal engineering has to give away is if you look at this process, right? And you get into detailed design. So you're starting at project identification, and we went in the first lecture talked about writing a Gantt chart. If you have no idea what you're doing, it's really tough to write a good Gantt chart, right? So you guys all wrote a Gantt chart after that week, or at least considered doing so. You at least thought about it, right? you realize if you're doing a project that is unlike anything that's been done before, or unlike anything you have personally done before, it's really tough to know how to get there, okay? So there's this concept called Emergent Design. And what this is basically saying is, I don't know how to execute this project yet, okay? So if you're making the 5th iteration of something that exists, right? If you're an engineer for Nike and you're creating a new pair of running shoes, you should have a really good idea what you're doing, right? Because you've made running shoes for 40 years or something. So you should know what you're doing. But if you are coming up with something that doesn't exist before, so here's an idea of mine if anybody wants to patent this, right? Roof tiles for your house that flip from dark to light with the seasons. So in the summer they're dark, or in the summer they're light, reflect light. In the winter they flip over, they're dark and absorb sun, right? Help heat and cool your house. If you're designing that, none of you have any idea how to design that today, right? Is it gonna be like some kind of electronic thing that flips, or is it gonna be a mechanical flip, or you don't know anything about roofing materials or how to build a roof? None of you know how to do that. So if I asked you to write a Gantt chart right now, you would do it and it would be really bad and really inaccurate, right? You should do it anyway, even though you don't know, so that you can update it as you go. So if you're in that situation, it should be bad. If you're engineer at Nike, it should be good. So emergent design is, I'm gonna start working because I don't know how to do this, right? I'm building a project with an Arduino. I've never programmed one before. I don't know how long it's gonna take me. And what you do is update as you go. So you be upfront and honest and say, I don't know, but I'm gonna update it as I go. So a good analogy of this, if I asked you to go from Virginia, or let's start at St. Louis to Oregon today, you guys would look at a map. Well, you guys would use your phones or something, but if I didn't let you do that, right, you would pick a route through the interstates here, and you could timeline that really well, right? I'm going 80 miles an hour because I drive too fast, and you could get a really good budget, okay, because you would know how much gas you're going to burn over that mileage in the car that you have, things like that. And you could come up with a really great project plan. So you could design this trip right now, okay? Now, if you were Meriwether Lewis, right, in 1805, I think it was, this is the best map of the United States that you have, and you're going to Oregon, okay? What's your route? How do you get there? How much is it going to cost? How long is it going to take? What kind of supplies do you need? Right? This is where you guys are standing when you go to design stuff that's never been made before or that you've never made before, okay? When I ask you to go and build a Braille reader out of Arduino, you don't know how to do it, right? So it takes some time to learn. So emergent design. So accept that you don't know. And if you get into an industry after this that you have that situation, be grateful because you get to be creative, okay? So, you know, Meriwether Lewis and Clark took the Mississippi River to the Missouri to the Platte River, and then they crossed the Continental Divide and went down the, I don't know, river on the other side. I don't remember. But they had no idea, right? To put yourself in that situation, you've got to pack for that trip. Good luck, right? So they brought some interesting things, but you get the concept, right? So here's the engineer at Nike building a new pair of shoes. I know the features I want. I know how to get there. And then, you know, here's the person building the roof tile. You don't know how to get there. It doesn't exist. So that's specification development. A couple of things I want to cover now. We've got about 15 minutes left, which is pretty good. First, functional decomposition. So this is just another tool for you guys to use to make sure you've got all your specs. It's a good one. I hadn't really used it before I came here, but it makes good sense. And then jump into a little activity on building a spec sheet. That white doesn't show up really great, but so functional decomposition, basically you're just taking your product, you're going to break it into the basic functions, right? And then you're going to want to keep breaking those functions down more. So if we're talking about a coffee maker, right? The basic function of the coffee maker is to make coffee. And then you can break that down. Say, my coffee maker needs to store and heat water. It needs to store and grind coffee beans. It needs to brew the coffee and keep the coffee warm, right? So those are kind of the functions. You keep breaking it down this way. And then you want to keep breaking it down as you go. So next you'd say, okay, I need to store and heat water. So you want to say, I'm going to store water and heat water. So you can keep breaking it down into like a big tree, okay? And this is a great way to look at your specifications at the end and see if you got them all. So this is more at a user need level, right? This is what the user needs. And then as you break this one down, you say, okay, I want to store and heat water, so I want to store water. What's my specification? Right? Store water was as specific as I could get that down, right? How much water? I would need to store 1 liter of water without allowing it to evaporate, things like this, right? And they say, I want to heat water. I want to heat how much water to what temperature? I want to heat my 1 liter of water to 200 degrees, whatever it might be, okay? Same thing, store and grind coffee. How much, how long should you be able to store it? So that's when you want to get into the specification phase, okay? If you're looking at keeping coffee warm, how long should I keep the coffee warm? What temperature should it be? So that's where you can write specifications. Does that make sense to everybody? Okay, good. Okay. All right, now we're going to go into a little revisit from last week. This looks awful. This looked a lot better on my wide monitor. I guess let's just start zoomed in here. So this is kind of a basic outline for a table. Sorry, this looks really bad on this monitor. A great way to store these documents. So that if you go onto the EPICS website and you click on current students and then you scroll down to the design document, everybody's keeping that document up to date, right? Yes, yes. If you're not, you should do that now. EPICS website, current students, is where all information that EPICS students ever need resides, at least Purdue EPICS students, okay? So go there and look at the design document. So none of you have seen this before, right? I will show you. This is important. So I will take a moment to show you where this is. Because all these lectures that you guys have been going to really feed into, I don't know why this comes up to MSN when I log in on these computers. So Google or Bing for EPICS, and then click over here on the left-hand side at current students. And this is the home of all valuable information, okay? So like when you go into your lab each week and your TA tells you that something is due, you can find that here. When we tell you to go in and watch the tape lecture of lecture today because it was so good you wanted to see it twice, you'll find them here, okay? So all that stuff is here, your syllabus. This week in EPICS, there's just kind of a copy of the emails that Dr. Zoltowski sends you each week. And if you go into guidelines and templates for teams and individuals, very long and descriptive title, then you have the second section here is design documentation, okay? And there's a guidelines, which is kind of a Word document on how to do it, and a template, okay? Okay. So this is the design document. All of you should have one of these for your projects after today, right? So this is really simple, okay? It's like 18 pages, okay? And a lot of that is headers. I think I told a few of you in the first lecture, the last set of design documents that I did for one project, which was a relatively small project in my last company, was 4 4-inch binders of paper, right? So 18 pages is okay. This is the least documentation you'll ever have to do, ever. So here is the basic structure of it, but what you're really looking for is section 5, the overall project design bit. So section 4 is important, like once when you do the project charter. So those problem statements we talked about should go in there. So this is just summary of the rest of it. So here goes your project charter. Here's who my community partner is, who the stakeholders are, right? We talked about stakeholders last week. Project objective is basically that project definition statement. Your timeline, here's where you attach that Gantt chart, right? So everything I've been talking about with you guys follows the design documentation. So as you go to these lectures and you fill out all those documents that you make on your own, they tie back here. So this last piece, section 5, it goes in reverse order, which is confusing to me. So if you scroll down to phase 1, this will give you project identification phase, okay? So these are the things we've been talking about. And it'll ask you things like conduct a needs assessment, right? That was what last lecture was all about. And then it says evidence can be found. So this is where we make it really super easy for you guys because we don't have templates that show you it needs to be 400 pages or something. You can just write a Word document, write all your user needs, done. Okay. And then as you head up into more complicated pieces of it, specification development is where we are at right now. So you're going to do here. Yeah. So we got lots of boxes here, but when you get down to this one, is the important one. Define customer requirements, or the next one, develop specifications document. So that's what we're talking about today, specifications. You can make all those in one document, and that's what we'll show you I will show you in the example in just a second. And it makes it really easy because then on this evidence thing, you name that document something like, I call it a risk input-output table because that's what we called it in my previous company, but say see our user need matrix and put all your user needs and specifications, everything in it, and just point there. And then when you hand this document in, it's all really straightforward, okay? So everybody should be going to this and filling this in. Everybody knows where to find it now? Anything else that you don't know how to find I can show you real quick? Okay. All right, so we got about 10 minutes. So this is, I call it a risk IO table. You can call it whatever you want. I don't have the risks in here, so that's a little bit funny. That would be the next part to do, and we'll talk about that after design reviews. So if you guys come into the second half of this lecture series after the midterm design reviews, we'll talk about verification, validation. We'll talk about design outputs. So everything we've been doing up to now is like before the active design, and then the active design is kind of it's a natural act, right? So you do user needs and specifications, and then you design, and that's where you guys are creative and you come up with all this stuff. And at the end of that design, you create design outputs. So that's your prints and your schematics, all those kind of things. And then you do verification, validation, and then you build the thing and send it out the door, right? So if we come in here to user needs to begin with, okay, so Purdue Kite Company, our project was that cool new kite for our fall line for all the winter kite flyers. So user needs, what were some of the user needs that we came up with last week? You were all here, at least almost all of you. And I made all of you write down a user need. Give me one. Okay.
Must be able to fly.
Fly, yes. Must be able to fly. Fantastic. Okay. So that is a user need. Very good. So fill in a user need. If you guys want this template, I can send it to you. You could make it yourself in 30 seconds. It's not too tough. So it must be able to fly. So let's create some specifications for that, okay? So that's my user need. I'm gonna come in here and say, I said design input, same thing as specification, sorry. I call that a specification so I don't confuse you with terminology. I told some of you last week that this terminology is really cluttered in industry and academia, I think. But you get the concept, right? It's all the same thing. So it must be able to fly. What are some of the specifications you would have for being able to fly? Go ahead. Fly 50 feet in the air. Now we talked a little bit about considering your environment of use, right? So if you say that it has to fly 50 feet in the air and you don't tell me anything else, then you better be able to fly 50 feet in the air in a hurricane or in no wind whatsoever, right? Can you design that? I'd be impressed. It'd come with a sweet fan or something to blow it up in the air. So do you want to qualify that? In wind speeds between 10 and 20 knots or something, I don't know. You prefer miles per hour or meters per second, or we can go with knots. That's nautical. All right. Okay, so that is a good specification. Can you test that? Absolutely, right? So you might have to go in a wind tunnel to do it, right? But you could set a wind speed, or you just wait for that right day and you can measure that. Okay. Give me another user need. Be able to control it. So. Okay. Control height and direction. Okay. So then we're going to come in 2.1. Okay, what are some specs for height and direction? I need to control the height. Did you control the height? How are you going to measure it? Okay, so you want to specify the reaction time of the, okay, that might do it. Should be able to raise no slower than 10 feet per second, right? So that's a good one. Do you have another one about, okay, so direction, we want to be able to change the angular direction relative to the user and no slower than 5 degrees per second. It doesn't really matter at this point, right? Because we're not designing a real kite, but you're getting the concept. Okay. Is this making sense to everybody? Okay. So you're going to go through and do this same activity. So if you will do this in your projects, and you can go through and do this. Now, the next line here that I have is source. This is kind of optional for you guys, but it helps in your documentation to know where things came from. So your user need of must be able to fly. What did we talk about last meeting about ways of obtaining user needs? How do we obtain user needs? Interview, right? So user interview. That's a great one. And then we're just come up with a spec. Other than that, I made it up. Right? So it could be from a standard. That'd be a great, if there's a Kite standard, that'd be a great place to get that from. That'd be the best place to get it from, actually, right? Maybe you did an analysis of Kite aerodynamics or something, right? So you might write that document out. If I can spell analysis. So the more you can document these things, so you in your note, maybe you just wrote in your notebook and you sketched out and did a quick free body diagram and figured out that this is where it should be. Or maybe you asked your user, or wherever it came from. And that way, when somebody says, why in the world does it need to go fly between 10 and 20 knots? That's not enough wind to blow a kite. It should be between 50 and 100 knots. I don't know how fast a knot is. Right? Right? So when someone asks you that, you say, well, I talked to 20 users and this is what they gave me, or I did this analysis and this is what I determined, right? So that's where you can defend that information. So putting in a source is a great activity. And then when I talk about verification and validation, we'll get into this in a little bit, but you'll have a design output related to these things. We'll skip that for now. We're going to talk about that not next lecture, but the first one after design review. But verification follows your specification, okay? So I said it should fly 50 feet in the air between 10 and 20 knots. So I'm going to test at 10 and 50 knots using standard procedure. And then you're going to want to tell what the standard procedure is, right? But so that procedure is that you hold a kite out with your arms like this, and you let a little string out and let it, right? And so you're going to find a day with 10 knots and a day of 20 knots and measure it at the boundary conditions, okay? So that's kind of the way you do this. And then validation comes off your user need, right? So you're testing at 10 and 50 knots, must be able to fly. You're going to have a user go out and fly the kite and say, see, it flies, right? So validation is all about user needs. Verification is all about specifications. Does that make sense to everybody? So 2 types of testing for every product, verification and validation. Sometimes they can get really cloudy, okay? But if you map it out this way, people will always understand what your user needs are, what your specifications are, and how they map up, okay? That is pretty much it. Do I have any questions? Everybody comfortable with specifications, user needs? So if I give you a quiz next time and ask you what is a minimum viable product, everybody can define that? If I ask you what is a user need, everybody can define that? Specification. If I gave you a set of specifications and said pick the best one, you can do that, right? Because what are you looking for when you're evaluating them? Verifiable, right? Non-conflicting, right? Yeah, unambiguous, yeah, right? So those are good. All right.